They did more than that. At the time that I read them, I was sort of wandering in the desert in a certain amount of despair at being unable to solve a problem that I cared about a lot. And when I read his papers, they inspired me. That this was a problem that other people cared about, that there was a way into this problem. So they led. I don't think that I would have gotten my PhD or be a professional researcher if I hadn't had Paul in my life and subsequently served on my thesis committee. So I was really happy when the ICFP organizing committee asked John Peterson and John Hughes to put together a tribute to Paul's life. And that's what we're going to hear now.
Thank you, Olin. So, we want to talk about our friend Paul this morning. And I thought I'd like to give you an overview of what he did in his entire career. But Paul has a publication list as long as your arm. So how do you grasp the totality of all of that work? Luckily, I have an app for that. I took all of his paper titles and I fed them into a word cloud builder. So here it is. Paul worked on functional programming languages. But there are other things here in here as well. There's Haskell, of course, but there's distributed systems, memory, FRP, some of the things that we'll talk about during this session. I also discovered Paul had 2 to the 6 collaborators and 3 queued PhD students. And these numbers say something to me about how nice he was to work with. So let's start at the beginning. Paul was born on July the 15th, 1952, in Baltimore. And his 6th birthday was a very important day to me. That's the day I was born. And also Bob Harper. There's something about that date. But maybe Paul didn't notice this dramatic event. He went on to Nashville, to Vanderbilt University for his bachelor's, and then he did his master's at MIT. And I found a copy of his master's thesis. But it wasn't about functional programming. It was about music comprehension. What does that even mean? Well, what it means is that Paul built a system that could take a tune, a collection of notes and durations, that's all, and it would kind of listen to the tune, and using heuristics that Paul had derived from human experiments, it would figure out where to put the beat and what the time signature was. So it would kind of understand the tune in that way. There was some functional programming in the thesis after all, though, because Paul built the system in Lisp. And he had this to say about his choice of language. I've found, through personal communication with other programmers in the Artificial Intelligence Lab, that many people begin their programming in Planner or Conniver only to find that the features they wanted most could be simulated in Lisp with much more efficiency. I suffered a similar fate. It seems the 2 languages are full of good ideas, but there are just too many good ideas. There probably ought to be a simple way to sever off the desirable properties of either language for specific applications. If only we had domain-specific embedded languages. I like finding that idea already in his master's thesis. This was 1974. So after graduating from MIT, Paul went to work in Maryland in industry for 5 years. But we know nothing at all about that because this was top secret. No, really, Paul had top secret security clearance. I think it was something to do with intelligence gathering, but nobody knows. Luckily, after 5 years, that was enough for him, and he came back to Yale. Sorry, he came back to do a PhD in Utah.
Okay, so Paul has decided now to move on with the academic part of his life, and he chooses the University of Utah. Well, why? Why? Well, so when I came to Utah, I asked around and said, well, what other students go out and go skiing and rock climbing and things like that? And the answer was Paul. Paul is the man. And when I was there, he was known for being able to get up to the ski resort and go skiing 100 days every year. And this is while he's doing his dissertation and all the other stuff. He is skiing constantly. He's backcountry skiing, he's resort skiing, he's on the ski patrol, and when he's not skiing, he's climbing and doing all these things. And also, another thing that he was doing was he was on a hike with the Wasatch Mountain Club, and he met a woman on this hike that became his wife. And so Paul actually got married the same year I did, and I was just honored to know Paul and Kathy when I got there. So here I am at Utah, and I'm doing stuff, and Paul is doing different stuff, and he is working with Bob Keller. So Bob Keller is Paul's thesis advisor, and he's part of the Applicative Multiprocessing Systems group. And so their goal was to make things go fast, to understand parallel computation in a functional setting. And so as Paul is doing this and skiing and playing music and all these things, he's finally able to graduate.
So after a few years in Utah, then Paul published his first paper in the Lisp and Functional Programming Conference in Pittsburgh in 1982. I remember that conference well because there were a couple of other guys who had their first papers at the same conference, like this one, and indeed this one. But what was Paul's paper about? Well, it was about garbage collection in a distributed system. So Paul was imagining that in amps there would be a number of nodes, each running a mutator and a collector at the same time. And perhaps unusually, all of these nodes shared one big virtual address space. Paul wanted to figure out how to do garbage collection in that space. You could have pointers, that is, between any pair of nodes. So Paul came up with a parallel mark sweep collector, where you would spawn marking tasks, and then, like Dijkstra's parallel algorithm, then nodes would be white before they were marked, they would turn gray while you were marking them, and then eventually they would turn black. And since Paul couldn't use a stack to keep track of the nodes that were being marked, he instead constructed a marking tree of back pointers as the algorithm was proceeding. So that was one of the new ideas in the paper. And then eventually you would end up with everything marked. Now, of course, while the collectors were running, the mutators would be modifying the graph as well, and the mutator could screw things up for the collector. So in this situation, for example, where we're in the middle of marking A, we've spawned a marking task on B, but it hasn't actually run yet. If the collector does this, if the mutator does this, now suddenly BC risks not being marked at all. So Paul thought about this, and he came up with a couple of invariants to guarantee that the collector worked. The first one here says, for each gray node, there must be at least one mark task spawned on each of the children. And here you can see, for the node C, that's not true. So this invariant tells us that to maintain the invariant, if the mutator does that, it has to spawn a mark task at the same time. And then there was another invariant about black nodes pointed to white nodes. So there were two cases in which the mutator had to help the collector a little bit. So Paul came up with this algorithm. He published the paper. He proved it correct. But to make really sure it worked, he also ran a bazillion random tests. A man after my own heart. So after that, then he returned to, then he moved to Yale, where he took up a position and remained the rest of his career. And very quickly, he had Presidential Young Investigators Award for research in analysis in support of parallel computation. Look at that, it was parallel computation that he was getting his research grants for. I want to highlight one of the papers that came out from that period, Memory Coherence in Shared Virtual Memory Systems, and this was in Principles of Distributed Computing in 1986 with Kai Lee. And I want to highlight this one in particular because this is Paul's most cited paper, even though it's not explicitly about functional programming. And what's the idea? Well, the idea was, if you think back to his first paper, he assumed that you had this distributed virtual memory that all the nodes shared. Well, how would you implement that? That's what this paper is about. The idea is that if you combine the virtual memory hardware that the nodes had anyway with a cache coherence protocol, then you could have an efficient virtual shared memory. Okay, so what's the idea? If you've got a number of nodes, A, B, and C, and maybe they each have a copy of a page, that's fine as long as the pages are read-only. And as long as they just read, they can just keep doing that. No problem. But what if one of them wants to write to that page? Well, in that case, before allowing the write, you have to invalidate the other copies, like a cache coherence protocol, and now you can turn on write permission for that page on node B. And node B becomes the owner of the page. That's fine until somebody else wants to, say, read the page. So if A wants to read it, well, now A needs to fetch the page from its owner, and at the same time mark it read-only on both nodes. And now if A later writes the page, then just as before, it's going to invalidate the other copy and mark the page owned by A now. Okay, so now, watch this carefully. What happens when C wants to read the page? Well, of course, we've seen this already. It has to fetch the page from A and turn both copies green. But the question is, how does C know where the owner of the page is? How does C know where to get the page from? Well, you could have a central service that just tracks where every page is owned, but that's not very scalable. So what Paul realized was that C could simply remember the last owner of the page that it knew about. So the last time C knew anything about this page, it was when B wrote it. So C can record, well, B is probably the owner of this page. But of course, B isn't. The last time B saw the page, it was when A wrote it. So B knows that A is probably the owner of the page. And by following these probably owner links, you will eventually find the page. In fact, eventually won't be very long. At most, you can visit each node once. And if you have to follow one of those chains, as you're following it, you can update it so that all the pointers now become correct. So it turns out that you can keep a mostly correct idea of the owner of each page and end up with an efficient implementation. So Kylie and Paul did some nice benchmarks. On one of them, they even got superlinear speedup. This is for PDE solving. You might wonder, how can the solver run faster, more than 4 times faster on 4 nodes than on 1? It seems impossible. But it's not. These were algorithms with quite a lot of data. So on 1 processor, they'd start paging to disk. 4 processors have 4 times as much memory, and so you're much less likely to need to use the disk. And that's how you could get superlinear speedup. So this was an extremely significant paper, and it actually won a SIGOPS Hall of Fame award. It spawned an entire research area and introduced cache coherence mechanisms that are widely used in industry. So a tremendously important paper. And it shows how important parallelism was to Paul. And he kept working on that for his whole career. So just 2 years ago at the Haskell Symposium, then he was co-author on a paper about a new I/O manager for GHC. They discovered that GHC didn't implement web servers in a very scalable way, and it turned out that the I/O manager was a bottleneck. So by carefully tracking down where those bottlenecks were, they managed to improve the performance of a web server on 20 cores by a factor of 6.5. And they applied it to a software-defined networking server as well. And this was a comparison of scalability up to 40 cores between SDN servers in Haskell, Java, and C++. And yes, this is the Haskell. Look, more than 20 million requests a second. I know you won't rest until you know which the other 2 are, because one of them is clearly much better than the other. And actually, it's the Java that was much more scalable than the C++ in this case.
So when Paul arrived at Yale, he found that there was a group of students that had lost their advisor and were looking for a new home. And so this is the T group over here that is working on compilation of Scheme. And so it's not quite pure, but it's certainly a functional language. And So Paul sort of took these students in and adopted them as his own, and this led to another classic paper in the literature. So, I hit it. So this is the Orbit compiler, and after after they came to Paul, Paul was able to advise and graduate most of these students in one way or another, and to also help them make an impact with their research. And so this was a major accomplishment on his part. So it was the best scheme piler for many years. It was something that made aggressive use of CPS. It's something that was able to outperform C on some benchmarks. And it was also the basis later on for the Yale Haskell compiler. And so when I first came to Yale, I was working on the Yale Haskell compiler, and we were using Orbit as our backend and doing a translation of Haskell into Lisp, and then Lisp would get compiled by Orbit. This worked out very well in one sense. So we actually had a functional Haskell compiler up and running, and it was interactive. So we had GHCI, but unfortunately, our dependence upon Orbit and Lisp in general turned out to be the downfall. And so unfortunately, Yale Haskell sort of faded away as Lisp was not being ported to new machines and new operating systems. So
in the early days at Yale, Paul designed his own programming language. Everybody did in those days. I've got a couple of fragments here. It had some interesting features. You could, for example, pattern match on expressions. So this function, one less, actually it returns true if you give it two arguments that differ by 1. So x will match 5 here, and, well, in that case, x plus 1 is 6. That matches the other argument. If you give it 5 and 7, you'll get false. So it had a rather idiosyncratic pattern matching. These are lambda expressions, or as we like to say, at equals expressions. There were a variety of unusual features in here. It was a little quirky, as many of these languages were. So then, just before the Functional Programming and Computer Architecture Conference in 1987, that guy, that's Simon Peyton-Jones, paid a visit to Paul on the way to FPCA, and while they were there, they got talking about this plethora of languages, which were kind of just, everyone had its own quirks, and you couldn't share their work and so on. And they thought, wouldn't it be a good idea to have one language to rule them all? And so when they arrived at FPCA, they called a meeting, the first meeting of the Haskell design process. And so everybody agreed it would be a good idea. It would be a simple matter just to unify the various languages that existed. And that led to a number of meetings, a lot of hard work in New Haven and London and Glasgow and other places. The first meeting, of course, had to decide the most important thing, the name of the language. And the method that we used was that everybody got a chance to write a name on the whiteboard. Lots and lots of names appeared. And then everybody got a chance to cross names off the whiteboard. And most of them were crossed off again. And at the end of this process, it was clear that the new language should be called Curry. But luckily, this was not at the end of the meeting, so there was time to sleep on it. And next morning, a few people were starting to have some misgivings, thinking about all the puns that would be made. And in particular, one of the very good abstract machines at the time was the 3-instruction machine, or TIM for short. Oh dear. So we realized that this was not a good idea, and the language obviously had to be called Haskell instead, after Haskell beat Curry. And Paul and David Wise got the job of asking Haskell Curry's widow if she would bless our use of Haskell's name for the language, and Paul actually went to see her, and luckily she gave her blessing. But as he was leaving, she said, "You know, Haskell never really liked the name Haskell." But by then it was too late. So there was a lot of work that went into Haskell, and Paul played a major role in that. He and Phil Wadler together edited the first Haskell report, although there were one or two scary moments. I remember the morning I went into work, and there was an email message from Paul, and it said, Haskell is just too much for me. I'm resigning from the committee, and I'm going to resign from Yale as well. I'm going to take a job as a musician. We were all kind of shocked by this. It was some hours before anybody noticed the date. So this was 1 or 2 years before the report was ready.
Yeah, the tradition lived on in subsequent years. There was a posting from Glasgow announcing the first Haskell compiler, which was available at IP address 127.0.0.1, and got a lot of people to actually FTP there to look for it. There was also a posting from Haskell on the Haskell mailing list that told about this miraculous thing that happened at Yale, and that the medical school had switched to Haskell from C, saving many lives. Of course, this was all Paul's joke on the community, but yet he managed to get a lot of people to take this seriously before they read the date. So another thing that Paul did at the start of Haskell was to make it so that people could learn the Haskell in some ways. Before all the Haskell books and so on, before the online tutorials, was the gentle introduction. So this was sort of the original path to learning about Haskell, other than reading the report. And only, unfortunately, it's not quite as gentle as the title suggests. But still, it was for a long time the way to find out.
So around about this time also, then IFIP Working Group 2.8 was formed. IFIP working groups, if you're not familiar with them, think of them as something like a regular informal workshop where a group of people get together to discuss a particular topic, in this case functional programming. And the working group was broader than just Haskell, of course, but many people involved with Haskell were members of the group and regular attendees. So there's Paul, for example. There's Simon PJ. There's Phil Wadler, looking distinctly hairier than he is now. There's me, looking slightly hairier. And so we would meet regularly. A lot of work on Haskell was done at these meetings. One of the nice things about the meetings also is that they're informal, they're 5 days long, and usually on the Wednesday afternoon we would get some time off. And then we would go and explore some local attractions. And this was when I learned how much of a mountain man Paul really was. Here we are, this was at a meeting in Washington State when we went up Mount Rainier on the afternoon off. Paul leading the way. I thought a straw hat was appropriate for the weather, apparently. Here's another one. This is Paul at a meeting that I hosted in Sweden. And I discovered that Paul was a consummate skier. He taught me everything I know about skiing deep powder, which is maybe not saying very much. But everything I know, Paul taught me. And he really outclassed the rest of us involved with Haskell, such as Simon here. And we would also hear about the work that was in progress. It was often at these meetings that I would hear about things Paul was thinking about. For example, he gave a talk about this. This only turned into a Yale Tech report, but I really love it. I love it in part for using the word munge in a paper title. I had to ask Paul what it meant. But what's it about? Well, it's about functional programs that manipulate arrays. So here's a little example where we create an array, we bind it to A0, we update the first element, select an element, update the first element again, and so on. And as we all know, the problem with this is that updating an array, in principle, requires copying it. And so every update would take linear time in the size of the array. And that's slow. So, of course, what we all really wanted to do was to munge the array, but only if nobody saw us do it. Just imagine the embarrassment as a functional programmer if you were caught out munging a data structure. So Paul's suggestion was that we write this code instead. Oh yeah, right. So in this example, we could actually get away with it because the programmer doesn't look at the first element after it's been munged. But if the programmer could easily refer to an earlier version of the array and thus detect the bad thing that we did. So Paul's suggestion was that we write the code like this instead. And here, what we're doing is we're using an abstract data type of array operations in a continuation passing style. So the abstract data type is not arrays anymore, it's the array operations. And if you look at the code, clearly an array is being created and updated. But there's no name for it. The array is hidden away, where the programmer can't see it. And that means we can munge as much as we like, and nobody need ever know. So that was great. The first time I saw the idea of using an abstract data type to hide an imperative implementation of functional behavior. And of course, this was a precursor of today's I/O monad in Haskell. It was, around about the same time, or a little bit earlier, work was being done, but this was the first time I saw the idea.
So one of the things that always impressed me about Paul was exactly how he could get so much done and still have time for stuff like this. So this is a Canadian peak called Snowpatch Spire, and that's Paul and I at the top enjoying ourselves. This is a This is a peak in the Wind River Range called Pingora and Wolf's Head. And those of you that have been to Paul's office would notice that this picture of Paul climbing up the side of that was prominently displayed on the wall of his office. So all of this stuff is going on, and he's getting tenure at Yale, and he's writing all these papers and everything else. And so this is one of the things that made Paul so special, was the fact that he had so many things that he could do well at the same time. Speaking of which, so in New Haven, he says, well, you know, just climbing and writing papers and Haskell, that's all fun, but I want to play music. And so he formed a group, and he spent many years playing, you know, actually getting paid to play music. And they cut a CD. They had a great time, and you know, that was Paul. Now, meanwhile, back at Yale, the Haskell group is part of a DARPA program to sort out what languages are good, which language should be used for developing software. And so Haskell has just come out, and we're able to sort of stack up Haskell against other languages of the time. And so we had hired on a new research scientist, so Mark Jones joined the group, and Paul and Mark collaborated on a problem that was presented by DARPA. And so this problem was one in which there are all these things sitting around, and there's geometries talking about sort of who's in control of what. And the goal is to be able to describe these geometries and to be able to determine what's going on and where things are. So this is the sort of thing that has to be computed. So we then get all these different people that are advocating for different languages to code this. And Paul, in the Haskell world, is able to use the techniques of functional programming. So we have regions, which are functions that take you from a point and determine whether or not you're inside the region. We have the ability to create primitive regions. So there's some geometry that says whether or not I'm in a certain circle. We can also complement that by saying, well, you know, we can take the result and negate it. We can merge things. So we have this idea of taking two regions and having a compositional style of programming. So having done all this, and we can create, we can create abstractions, right? So we can create a new kind of region by combining other regions. So in the end, all these languages are fighting it out. So you can see that C++ is not doing so well as far as the number of lines of code, even though it is a language that is well suited for other tasks, I heard. You see Ada is in the fight. There's some languages that no longer exist, but there at the top is Haskell. And you'll notice that Haskell is doing great. Now, DARPA was sort of wondering about this. Should we believe these people? Do they actually know what they're doing? And so they sort of had sent a secret shopper into this. And so that last one, they had found some poor victim that knew nothing about Haskell, trained him up and said, okay, spend a few days reading, of course, the general introduction, I'm sure, and figuring out how to do it. And so an untrained Haskell person ends up being able to do this in roughly the same amount of code that Mark Jones had been able to do, and had beat out almost everything else without any prior training in Haskell. So this was a convincing demonstration of the declarative languages in Haskell. So let's see, yeah. Oh, and the reason that was so long is that Mark had included all sorts of type synonyms and type signatures, and if we would have only taken those out, we could have gotten this to about 50 lines. But then again, that's the story. So, of course, the reactions aren't always as good as you would like them to be, even when you demonstrate to people the clear superiority. There was this sort of suspicion that maybe Haskell isn't a program, it's just a specification. And even though it's an executable specification, that's not quite the same as an actual program. Or it's a little too cute. Well, we thought it was cute too, but for some reason they don't appreciate it. Anyway.
So I just want to highlight a few of the papers that were coming out around this time that have been really influential. One of them was the paper on monad transformers and modular interpreters. So the idea behind this paper was something that was already known, that monads don't compose. So if you have a state monad and a maybe monad and you want to use them both together, there's no way of just combining them. But if you use monad transformers instead, then they compose together, no problem. And you can even compose state and maybe in either order, and you get different behavior as a result. So this was already known, but in order to make this really useful, you have to figure out how to express all of this in your programming language, Gopher in the case of this paper, and also how to take the various operations that are the reason you're using the monads and lift them to the top level so that when you combine state and maybe, in the combined monad, you can use all of the operations that either operator supplies. So this paper showed how to promote and lift these operations in some new ways, and how to build a modular interpreter where you had an interpreter for the state part of the language and an interpreter for the exception part of the language, and so on. And each part was entirely separately defined. So this paper is the basis for the monad transformer libraries that we have in Haskell today. And how important are they? Well, let me say this. If you're using monads in Haskell and you're not using monad transformers, you're doing it wrong. It was that important. Something else that Paul did at the time was he was arguing very cogently for embedding domain-specific languages in Haskell. And when I saw this, for me this was a new way of thinking about combinator libraries, thinking of them as defining a language. Paul wrote a number of papers on this topic, and he gave a keynote at a Usenix DSL event. And I think his thinking has had a really, really huge influence. I mean, nowadays, the thought of embedding a DSL in Haskell or in Scala or another functional language is part of our culture. It's in our bones. And that's thanks to Paul.
Meanwhile, this is the North Cascades, not too far from here, actually. And as Paul and I are going out to a Microsoft event, we go over to this is a place called Forbidden Peak. And Paul, this was a very special climb for Paul because he was able to bring his 12-year-old daughter along. And so not only is he climbing these things, but he is instilling in his family the desire to go outdoors and to do things and to not just have work and also to have this in their life. Now, while we're sitting around there at Yale, sort of out of the blue, Paul is contacted by this guy that we had never heard of. I mean, he really wasn't part of the functional programming community or anything like that. And he said, I've got these ideas. I've got these great ideas. And I think that my ideas would be best served with a language like Haskell. And so next thing you know, Connell has come out to Yale, and Paul and Connell sat down and worked on this paper. And so although Connell had the basic ideas for this earlier, so we had a system called TBAG that had the idea of reactive programming, when this was moved over to a Haskell context, suddenly all sorts of good things happened. And so one of the good things that happened was a MIP, which I suppose means most important paper.
Most influential paper award 10 years later.
Or influential. There we go. See, this is what happens when somebody else helps you with slides. So this led to a topic that the Yale group started to work on at length, and also is still going on today. In fact, I think there's a talk today about something like this. But the idea was that we wanted to go in and sort of bring computing to life. So ordinary computing, you just create values and they just sort of sit there. But in reactive programming, all of a sudden values start to sort of move. You have this idea that as time passes, the values change. And so it was all captured in this great signature, which says that a behavior of A is something which, as time changes, we see different values of A. And so instead of having programming where we're having to sort of recompute at every time step and there's an explicit update, instead we are over in the world of map where we're talking an entire sequence and manipulating the entire set of values as opposed to individuals. So we have all sorts of event programming that suddenly goes under the hood. So although the event stuff is probably there in the implementation, we don't need to write the event code. The event code is simply a consequence of the semantics of the language. So this is a classic domain-specific language where we take a mechanism and make it implicit inside the language. So we have things like time, which just says, hey, here's what time it is. And then we can do things that allow us to do, for example, wiggling, right? So that's just the sign of time. And so we can take a picture, and so all of a sudden now we're talking multimedia. So one of the things that attracted Paul to this was the idea that we could get Haskell into the world of multimedia. And so now all of a sudden we're able to define animations, we're able to define all sorts of things that were hard to define earlier. And so we have all these different things. And this is the original Fran implementation, and this is all of Connell's kids, who are now quite a bit older. And we can constantly compose things, right? So we're sitting here creating a composable framework in which these different behaviors can be combined in an elegant way, in a type-safe way, and yield more complex behaviors. So we also have events, and so left button press is when the mouse happens, and so this will tell us things. And we can create a switching behavior that says, well, do something, and then when an event happens, we'll do something different. So the event will tell us a new way of behaving, and then after the event occurs, we have a different behavior. And so we get the ability to have a reactive program where outside events are shaping the behavior. So in this case, we're having a color change based on the mouse. And then we finally have this idea that given that we have all of these motions, we can look at the timing. And so that delay anims is a way of capturing something at a previous value, right? So we're sort of looking back in time. We have integration, we have physics going on, we can do collision detection, we can do all sorts of great things in the context of this simple semantics.
So this was the first ever paper on functional reactive programming, and that, I think, was a really beautiful and fantastic idea. Paul alone wrote 20 more papers on the subject. So you can see what a productive area it was. I just want to highlight one problem that some of those earlier papers solved, and that is, if you think of having a value that refers to a behavior, well, it captures all of history. in one go, which is kind of great for expressiveness, but it means that a user might use that behavior to ask, well, what happened at the beginning of time? At any time during execution. And that means no garbage collection. So you'd be running these reactive programs. You could never garbage collect a thing. But of course, what you would want to do is just delete the past anyway. Munge the past, as long as nobody can notice. And that led to a new version of FRP called Yampa. So the idea here was, writing a function of type behavior A to behavior B is dangerous because in the body of the function, you might refer to behavior A at any time. So since these are dangerous to write, construct arbitrarily, why not abstract that type and define functions for creating these behavior functions? Here's a couple of them. Oh, look, arrows. It's using my work. Wonderful. But there you can construct a function. If you've got a function from A to B, you can construct a behavior function. You can compose behavior functions together. But the user never, ever can get their hands on a value of behavior type. And that means you still have the flexibility of expression, but it's safe to munge the past. And this was Henrik Nilsson, who was heavily involved in this.
So all of this stuff is going on, and in the background, Paul is saying, what have I done to help people understand my take on functional programming? And so this led to his work on this book. And so the Haskell School of Expression, actually he hated that name. He wanted to call it the School of Expression. And the publisher said, no, if it's going to be a Haskell book, you have to use Haskell in the title. So he ended up doing that. But this is a remarkable book in the sense that although he is showing you how to use the Haskell language, he is doing it by constructing a large set of domain-specific languages. So all of the things that he did with domain-specific languages end up in this book. The region code, the reactive animations, the music work that he'd done, all ended up in this book. And so this was a very different textbook from other books that were more about let's learn each feature of the language, let's look at examples which are sort of list of numbers kind of examples. He wanted the examples to be multimedia. And so here it is. Here is the reviews are in on Amazon, and people generally love it, except one. So, but you'll notice though that I like the second comment best because he is teaching you not Haskell, he is teaching you to think like a functional programmer. And so that was his goal, is to not teach a language but a way of thinking about problems and solving them. Now, another thing that happened after this was a program that he started at Yale called Computing in the Arts. And so Paul's view of computer science was that computer science was not a discipline that stands by itself, but rather should be part of many other disciplines. So he was able to bridge between computer science and, well, of course, for him, music, but also architecture, art, theater, all these things he felt had a strong connection to computer science. And so after many, many years of committee meetings and all sorts of stuff to get the approval done, Yale approved this and created a program in which the computer science department was actively collaborating with all these departments. So for example, an architect would be able to understand how to use computing to take data that was from scanning buildings and build 3D models of existing structures. And so this was a project done by a student that is interested in both architecture and computer science. So the idea, though, is that he saw computer science as a part of everybody's education instead of as being something that stands alone. And he felt that students in music and whatever would benefit by this. So the Creative Consilience is sort of the brand under which he's done this. And Paul was an essential part of this, and so he taught 2 classes, one in sort of algorithmic music and the other in sound generation that were part of this, but he also had time to supervise a lot of undergraduate projects. And so Yale undergraduates would say, hey, I want to make a new musical synthesizer, I want to be able to study music, and Paul would say yes. And so he had a chance to really spread the word of functional programming among many people. Now, in the meantime, he's also doing things like this. So this is Paul in the middle of the Grand Canyon. And this is a trip he took back in 2008 with his wife, Kathy. And it was a wonderful trip. You can see just how much he is enjoying himself. So this is Paul at the bottom of the Grand Canyon, just wearing his Maryland shirt, of course, and just enjoying it because he enjoyed life so much. So another thing that I think ties all of Paul's stuff together is the notion of service. Paul was there to help other people. And at Yale, the way to serve was to be a master. So Yale is different from most schools in the U.S. in the sense that they have residential colleges. So I usually explain these to people sort of in Harry Potter terms. So I don't know if this was Gryffindor or something like that, but he was head. And he would have 300 to 400 students under his direct control. He would be sort of the father figure to all these students. And as part of the deal, he and his wife lived on campus in an apartment directly underneath all these dorms. And so Paul lived right there and was in charge of all sorts of activities and simply engaging with all these students and being sort of a guide to their lives. So as part of his work on computing in the arts, he developed a new system called Utopia. So he had earlier created a system called Haskell for describing music in Haskell. And he wanted to generalize and make it a production piece of software. And they finally just released this just a little while ago, but it's really 3 different things rolled into one: note-based synthesis, waveform synthesis, and user interfaces. And that's Danya, who is currently actually teaching the classes that Paul used to teach. He is one of his last PhD students, as well as a gifted composer in her own right. So this is an example that Paul often used when he was talking about music. And what he's really doing is he is sort of celebrating functional programming. So he's starting out with a little function that takes a musical idea and a number, and it says, well, I've got 2 different ways of transforming. So every time you see the music A, arrow music A, you're saying something that changes music in some way. And so things like transposition or delaying or things like that are things that have that type. And so he says, well, let's start out with a simple little run of notes. That's good, but now can I make this more complex? Can I sort of artistically use the power of functional programming to get it? So now what's happened is he's taken a basic run, he's repeated it 8 times in this ascending thing, and then he adds a little bit more to it. And finally, in the end, in 4 lines of code, well, 6 lines of code, 7 if you want. He's created an interesting piece of music that has a lot of structure. And so he was all about finding structure in things and being able to exploit this structure as a way of understanding how things worked. As well as the MIDI level of things, he also worked on physical modeling. So this is a signal flow diagram that defines how a flute works. And so you can see there are delays here and there. You can see there are filters. There's all sorts of things going on. And you can see parameters in here that you can vary. And so you can create a user interface that allows you to tweak things like the delays and so on. And when you do that, it turns into this program using this horrible arrow notation that I don't know who figured that out. But in Paul's classes, students would learn how to take these sorts of things and put them together and produce sound. Did I do it? No. I'm poking. Right. So this is yet another another aspect of what Utopia is about. And then there's actually behind this a huge theory of what he called polymorphic temporal media. And Fritz Ruhr actually put this on a T-shirt for him, actually back before he named it Utopia. But you can see that he's got a tagline now. So Paul is putting the funk. Anyway.
So Paul was going strong, but at the end of 2009, then he learned that he had leukemia. And unfortunately, I mean, that can be better or worse, but unfortunately his turned out to be a very aggressive variety, which required a stem cell transplant fairly quickly. So a donor was found, and almost a year later, then Paul had the transplant, and it worked. It cured his leukemia. But this process has brought home to me that that's not like replacing a broken part in the car. This was just the start of a long series of complications. Nevertheless, the following August, he was able to go back to work, and he didn't let this stop him. So after the diagnosis, after the transplant, he wrote 3 more papers on FRP alone. He wrote the high-performance I/O manager paper that I mentioned earlier, and he wrote a paper on simplifying software-defined networking programming. So he was really quite productive. He was instrumental in setting up the farm workshop. He was the first workshop chair. He chaired the steering committee, and that's one of his legacies. And he was also working on another book.
So, as part of his courses at Yale, Paul was putting together a book called The Haskell School of Music. And he was unhappy with his previous book in the sense that the publisher owned the full rights to it. And so people were not able to really build on that book as a way of learning Haskell. It was simply a printed book that you had to go buy. And so he adopted a different model. And so this book is actually sitting on the Yale website for anyone to use. Unfortunately, this book is not complete. And so one of the things that is happening right now is that Danya and some other people are working to finish this book, and we hope to have this book in a publishable form and license it under a permissive license so that we can use it not just as a book but as content for people to adapt. And so I'm personally looking at adapting this book for beginning audiences as opposed to advanced functional programmers, but this is his sort of final gift to the world, is to take his joy in music and to turn it into a way of learning Haskell, a way of finding out about stuff. So one thing that I haven't had a chance to talk about too much is Paul's family. If you knew Paul, you knew his family. He would often invite the graduate students over. Ben Goldberg used to babysit his daughters and things like that. And family was very important to him. And so this is his older daughter on the right. That's Christina, who both of his daughters went back to Utah. And so he had bought a house in Utah. His daughters both went to the University of Utah. She has now got a PhD in clinical psychology and also has given Paul his first grandchild. And on the left is Jenny. And Jenny is actually very similar to Paul. She spent many years as a professional skier, and so this is her competing in the women's halfpipe event, and she actually gold medaled at the X Games. So
Paul had several more good years. He was at ICFP last year, but not long after that, then his health began to deteriorate, and in January he had to go into hospital. He was never to leave. For a while there, it did look as though he might be able to come home again. But around about The 19th of April, his condition began to worsen rapidly, and by the 23rd, then it was clear that this time Paul was not going to make it. And the machines in the intensive care unit keeping him alive were turned off, and on the 29th, we lost one of the most creative, productive, and nicest people in our field. Just going to end with some of Paul's music. Download that, it's on the web. We have a few minutes left. Questions seems a strange thing to have after a talk like this, but I'm sure that many of us have fond memories of Paul, and if anybody would like to share them quickly now, then you're welcome to do so.
I just wanted to say that even though I never worked with Paul, he was also the reason that I got into research. He came and gave a talk at Indiana University in 2001, and the idea of domain-specific languages and also FRP directly led to what I wanted to work on in my PhD. And I did have a question, actually, which is, how many people are here now who are Paul's students or grad students? If they could maybe stand up or whatnot.
I just want to add that Paul's also the reason I'm here. The paper on monad transformers was really influential. Including me, I tried to introduce it to linguists.
I thought I might just say how much, and when I was getting started in research, every summer I tried to make a sort of tour of the United States. So I would visit sort of Dan Friedman, and I always visited Paul, and I always regarded him. He was just a little bit older and quite a bit smarter than me, and so I found him a very sort of inspiring colleague. But he was close enough, unlike sort of Dan Friedman and David Wise, who were kind of like gods. So Paul was kind of accessible to me. So he was a very sort of encouraging peer. That and at a time when the lazy functional programming community was in this sort of insurgent phase, Dan Friedman and so forth had been writing a lecture, cons should not evaluate its arguments, and we were kind of like the kind of trying to upset the world, and then Bacchus wrote this paper that said not only was functional programming good, it really was going to take over in the world, and he was a Turing Award winner, so that was kind of like legitimizing us all. So it was quite a kind of exciting time, and Paul was kind of played a leadership role in making that sort of group of insurgents gel and congeal as people who collaborated together rather than people who competed and fought with each other. He was very good at that kind of community building stuff.
Okay, perhaps we have reached a conclusion. Do you want to say any more? Shall I just play the music again?